Right, welcome back, Physics 30. Today's lesson is lesson number 4 of the Unit C Part 2 booklet. It is known as Compton Effect. Like the word suggests, it is done by a scientist Compton. It was done in 1923, and this is one of the main discovery of light as a particle. So the approach was like this. Imagine a curling game. If you are, for example, sliding one of the rock and then imagine you're hitting another team's rock that is inside in the middle, the most center. During that process, you will expect that the momentum of the rock that was just slide will strike the rock that is already exists in the middle, and the outcome, even if you don't see what's gonna happen, you will know that it's gonna hit if you have enough of an impact, or rare enough it may stick together and travel together. But long story short, you will know that stationary rock will get strike and move. To what extent, that's when the calculation is needed, like P is equal to mv, something like that, right? And it can be two-dimensional for sure. Basically, he used similar idea. He found that, photon has enough of energy to dig up the electron and then send an electron to somewhere else, from cathode to anode in that situation when you think about photoelectric effect. So Compton's main discovery was based on the idea that photon possess momentum. According to the classical theory of explaining about photon is, well, the EMR has zero mass. And even at now, which we're going to talk about more in quantum mechanics situation at the later section of this unit C, it is on the right track. Massless object was believed as photon, and I do have limited knowledge about it, but so far I'm pretty positive it is still massless with a bunch of new theories. Therefore, photons should have zero impact, because as you may notice, P is equal to mv, and if mass is 0 kilogram, then you will know the outcome. They will be gone. 0 times something will be gone mathematically, and P will be gone. Momentum doesn't exist. However, Compton suggests that photon could have equivalent mass, and therefore they could collide with other particles. And he calculated the momentum of the photon as following: E is equal to Pc. Now, to be fair, this Compton part will be combined as Einstein's famous E's mc squared. But long story short, we are not in university course where we derive a formula from other scientists' formula and then combine calculus with it. We are not doing that. So in high school, you need to understand how to algebraically go through each of the situation. E is, of course, energy that measured in joule. P is what we know, basically. I know that traditional way of P, you have a little arrow on it because momentum is a vector, but let's just use it as the way it is: photon momentum, kilogram meter per second or Newton second. Doesn't matter which one you use, but the first case is way more common for momentum. This is more common for impulse, which is change of momentum. C is what we know of a speed of light in air, vacuum, 3 × 10⁸ meter per second. And based on this equation, whatever the EMR that have high frequency have higher energy. So X-ray, gamma ray, those kind of guys, or UV ray, those are the ones that have most momentum. So high frequency will have high energy, which will be high momentum. That is one of the relationship that Compton suggested, and his experiment was on the right track. So let's do this simple question. How fast would an alpha particle have to move to have the same momentum as 7.30 mega electrovolt photon? First of all, we have energy that is given, 7.30 10 to the power of 6 electrovolt. I want you to convert that into joule by multiplying with a elementary charge value, basically 1.60 10 to the power of negative 19. Then you will have 1.168 10 to the power of negative 12 joule. Now we're talking about photons perspective, so I'm gonna go with photon perspective as a first. Now let's find out momentum. Momentum is E is equal to PC, which means if I rearrange it, E divided by C. Then you will have 3 point, and we're going to round it up a little bit, 893 10 to the power of negative 21. It's a good idea to keep about 3 for a decimal place if you want. That is momentum possessed by that EMR with the energy of 7.30 mega electrovolt. Now the question doesn't ask you about that. The question is asking how much of speed does an alpha particle possess to have the momentum. So now we are talking about alpha particle. Now alpha particles mass and velocity, it's not a massless particle, so we're gonna go with P's MV situation. And honestly, you can get rid of these arrow at this point, but I'm gonna use it as traditional way. P over M. And mass of an alpha particle is 6.65 10 to the power of negative 27. Then you have 5.85 10 to the power of 5 meter per second. That is a speed that has to be possessed by an alpha particle to achieve this amount of momentum, which is possessed by the photon. So know what formulas to combine. Everything is algebra. Everything is algebraic method. In diploma questions, you will see algebra situation. Now let's go with our one of the most important one. In diploma, we always have Compton Experiment questions. It is one of the most important outcome and one of the most important supporting evidence. I don't know how much connection that Compton and Rutherford has. It's very similar experiment too when it comes to those two. People who remember Science 10, Rutherford had a gold foil experiment. It's very similar. So Compton effect. Compton basically used high frequency EMR. In fact, he used X-ray. Remember the relationship. Why he chose X-ray is because high frequency, high energy, high momentum. That was his connecting logical order, if you will. Compton directed high frequency X-ray directly to a foil. It was carbon. And when it comes to the Rutherford experiment, that was gold foil. But in any case, carbon foil. And when he sent that X-ray, if you are truly believing that this is massless, so photon, I'm going to draw each of the photon, then if it's wave, it should go through with no problem. Same direction, or it will be reflected back, maybe refracted, but shouldn't emit anything because there's no momentum. But unlike other physicists who support wave theory of a photon, as soon as that X-ray go through the carbon, yes, there was little deflection, X-ray that is deflected, but at the same time, like the curling example, we discovered that electrons also are emitted. There are some electrons discovered. So this result basically destroys some of those classical theory. It defies the classical theory in two perspectives. So, number one, the classical theory said there should be no refraction since the angle of incidence is zero. So what that means is, if you think about sine zero as an example, that means we're going to have zero. So Snell's law will lead to zero. Come to think of it, did I mention refracted? Sorry, I was trying to put reflected when I was talking about wave situation. Now, frequency shouldn't change, because as soon as you leave the source, that should be equal to whatever the frequency that you have after you go through medium and something like that. So frequency after leaving sources, frequency outside of the sources, that should be same. Now, however, what he discovered was X-ray energy. I'm going to put incoming energy and final energy. When you compare these two, incoming energy was higher. In fact, we found that X-rays has slightly longer wavelength. And this experiment was refutable evidence that electromagnetic radiation, light, behave as a particle. Because if you think about particle, like I said, curling stone that is going will strike the curling stone that was existing at the center, but after it hitting, the one that is traveled to strike the other team's stone should slow down. Very similar, very straightforward. This is like unit A situation. My momentum and impulse situation, no brainer. This solidified the fact that EMR has wave-particle duality. And in this case, it is particles for sure. So what's the formula? How can we calculate? Here's the thing. It goes with the conservation of energy and conservation of momentum. If you go to energy perspective, energy of incident X-ray, incoming X-ray, that is equal to kinetic energy for electron and X-ray final, which was generally higher wavelength. That's a one way of approach. That's a law of conservation of energy. Conservation of momentum situation is, well, if I have incident or incoming radiation's momentum, it should equal out with electron's momentum and my final X-rays momentum, which again, like I said, slightly higher wavelength because it lost energy. So it is two-dimensional situation. Although incident energy is 0 degree when it comes to encounter the foil, X-ray photon have what we like to call oblique collision with an electron in orbit around carbon atom. In this way, the photon was acting as a particle, and photon will go with certain angle over here, and the electron will travel with certain angle over here. The one thing that you need to understand is angle of deflection, or our reference angle, is always with deflected X-ray. We are not talking about the angle that is happening for electrons. So do not use the angle of deflection for electron. And when it comes to this angle, I like to put with respect to its initial direction. That's what I want to point it out. So, Like I said, we're not trying to derive equation to another equation. We just need to know how to use the equation that is found by Compton. Here's what it is. Delta lambda, which is, if you want to know, final minus initial. Simple as that. Delta means the difference of or change of. That is equal to h over mc. This mass, first of all, is mass of a particle, and generally it's electron. And 1 minus cosine angle, this angle, like what I emphasize a lot, it is X-ray photons angle. So have that in your mind. Now, let's deal with this question. We have X-ray that is incoming, and we have a foil. And of course, the initial direction goes west to east or left to right, whatever the method you like to have. The angle of electron goes 21.6 degree, which, like I said, we're not going to use it. But can you see the deflected electron go almost all the way back? So people time to time try to use 17 degree with, like how we did Snell's law, you know, incident angle, reflected angle, those kind of thing. But here's the thing. It's with respect from initial direction all the way to deflected. So the angle is in fact 90 plus 17, which is equivalent to 107 degree. And that's what you need to use. So here's what it is. The PM, this is picometer. So right now we have initial wavelength, which is 2.80, 10 to the power of, if you guys remember, nano is -9, right? Pico is another smaller level. So 9 plus 3 is 12, so -12 meter. We also know angle of deflection, 107 degree. We know mass, I believe it's an electron that is deflected. That's what we have. And we are trying to find our final wavelength. Know the fact that when it comes to final wavelength versus initial wavelength, final wavelength should be larger. Because, as you may notice, you should lose energy. So, let's start. First thing first, I'm gonna write down delta lambda as the way it is. Way it should be. Final minus initial. Final is equal to HMC 1 minus cosine theta plus lambda initial. And then punch the number in. I like to put a lot of bracket to make sure. An entire unit will be meter. Don't forget to change it into degree mode if you are in Math 30-1. So you have 5.94 10 to the power of -12 meter, or you can say 5.94 picometer. Like I said, double check. My final 5.94 is bigger than 2.80. That's a fancy way of saying my energy is lost. Now, determine the kinetic energy of an electron. Now, then we are trying to go with conservation of energy. My total energy initial, my final energy total should be equal together. I have X-ray incoming energy, which is equivalent to my kinetic energy of electron, plus X-ray final energy, something like that. We now know both of the wavelength. I can say HC lambda initial. We need to, we're not trying to find the energy of it. Speed of it. So I can just put EKE And if I move this to the other side, it would be better if I move this to another side. But anyway, X-ray HC lambda final, we're basically find the subtraction of it. So my kinetic energy is equal to H outside, actually HC outside, 1 over lambda initial minus 1 over lambda final. So there we go. That's what you need to do. And let's punch those numbers in. Then you have 3.76 10 to the power of negative 14 joule. Gotta say, I just found that my teacher answer sheet have a little mistake. The PDF file, I for some reason put 2.91, it's a 5.94, so I must look some weird number in there. Right, let's go with the momentum perspective. Sketch the vector sum diagram that illustrates conservation of momentum. Well, this is an easy part because electron, if you think about momentum perspective, I'm going to call PE final. You need to understand that's have PEX and then PEY, and those two perspective I have. And when it comes to momentum of deflected X-ray, same thing. I'm gonna put lambda final X, P lambda final Y. In this case, as you may notice, we don't have any Y components, so mathematically, my upper arrow, down arrow, they should cancel out. And these two, I can just say P lambda initial X should be equal to P lambda X final, P E X final. Can get to this conclusion, which provide me an idea how we can approach our determining X1 and Y1 situation if I use the previous, there you go, this conclusion. 50 A and S, this is atomic level, so that's why you have that A in front. That is equal to, and let's decide right and left as positive, same as up and down, up as positive like Cartesian plane. 50 is equal to, and we know our X-ray situation is positive 30 A and S, and we don't know what this X1 is. So just simply subtract 50 minus 30 A and S. So it is positive 20 A and S. That's my, if I like to say, PEX final. Y1, it should be very similar, except we don't have any positive or negative, so that means my Y1, when it comes to just absolute value, regardless of the sign, they should equal to each other. So that means my Y1 is actually 14 A and S, but it's positive, so it's going north, and that is equivalent to my Y components of momentum. That is today's lesson. Your to-do list is basically Going through the homework section related to this Compton effect, which is page 50 and 51, 52. There are 3 pages, that's a lot, so you can choose to do odd number or even number. If you like to do everything, I mean, I'm okay, but find your own balance. That's for today.